Hey guys, I want to explain why we select the weak axis for uh, to calculate the buckling load for columns. So we can just consider columns. So there are basically two types of failure in columns. If the column is short, generally it fails by failure of the material, or we call it by crushing. For example, say you have a column like this, so when you apply a load, okay, so when you increase the load, what will happen is the material will fail. It will reach the yield stress, and the failure of the column will take place generally by material failure. But if you have a long column, generally it will fail by buckling. For example, a column like this, so when you just increase the load a little bit, you see before it reaches its material failure, it will buckle. So it will generally fail by buckling. So I have just drawn cross section of a column, say for example something like this. So if it fails by this axis, x axis, it should fail like this. It's difficult, but if you consider the failure or bending by y axis, that's this axis, yeah, it's easily bent by that y axis, which is the weak axis. So if I just give some figures, some numbers for this one, just to explain this, say this is 10 millimeters. This is not a practical column or beam, just to show you the difference. Say this is 100 millimeters. So this becomes 10 and this becomes 100. If you calculate the I value using the major axis, which is x axis, so Ixx for figure A is 1 upon 12 BD cube. Here B is the dimension parallel to the axis we consider. So here we are consider bending about this axis. So the dimension parallel to that axis is 10. So 1 upon 12, B is 10 and D is 100 cube. So when you simplify this, it becomes 8.3 into 10 to the power 5. The unit is millimeter to the power 4. So now if you consider the I value along the weaker axis IYY, 1 upon 12 BD cube. Now B value is the dimension parallel to the axis we consider. So it's 100 now. 1 upon 12, B is 100 into D is 10 now, cube. So this will end up with 8.3 into 10 to the power 3. So just compare these two figures, the values we got for Ixx and Iyy. You can see this Ixx is in this case 100 times more than this Iyy, 10 to the power 3 and 10 to the power 5. So you can see always this Ixx is the stronger axis and Yy is the weaker axis. So this is true for any other section. For example, this is an I section, maybe a I-beam or universal column. So you can see, if you consider XX and YY axis, definitely you will get IXX much higher than IYY, because you see this flange is at a distance from the axis of bending, which gives a higher I value, not like here. So because of that, if you apply this Euler buckling load equation, so it's pi squared EI over KL squared. So when I is higher, the buckling load will be high. When I is lower, when you multiply by these other factors, buckling load will be less. So always we get the lower value for the capacity or the load it can carry, because it will fail by the weaker axis YY. So that's why we always take the weaker axis or the lesser value for IYY, value for the I. So this is the value you have to take when you are calculating the Euler buckling load. Thank you.